Okay, good afternoon, everybody. My name is Robert Moffett. I'm here representing Etherdyne Technologies, Inc., or ETI. We're a fairly new startup company that's working on wireless power. And today I'd like to talk to you about new possibilities that wireless power opens up in the field of structural health monitoring. So structural health monitoring is not my domain of expertise. And this is also the first time that I've been to this conference. So it's been very interesting for me to learn about all the amazing work that all of you have been doing on developing different sensors for structural health monitoring. And I've learned about all sorts of amazing technologies that people use in these sensors, whether they're ultrasonic transducers, strain sensors, accelerometers, etc. It's quite amazing to me to learn about all the data that you can collect and things that you can do once you can sense what's happening inside of a structure. So there are certain problems, though, that I've noticed when I've attended talks that seem to come up again and again, which have to do with powering these sensors. So I've seen a lot of people talking about the design constraints that batteries impose on these sensors, that you need to design the device to only use a certain amount of energy because the battery only has a finite number of joules available to the device over its entire lifetime. You have to optimize the communications system. You need to minimize the duty cycle of the device. You have to do all sorts of things in order to conserve your joules in order to get the device to last the intended lifetime. And so far, the only other solution to that that's available is wires, which have their own problems. So wires can limit the device placement. They can have other issues like interfere with the structural integrity if they're built into the structure. They can interfere with the aerodynamics of a structure if they're on the outside. So wires are not really a suitable solution in many cases. Plus, they also increase the installation cost if you have a very large number of sensors. So one question that I'd like to ask is, what could you design if power is no longer a design constraint? And what if you could get power without wires and without batteries? So this is where our technology comes in. So we've developed a system that we call the resonant magnetic loop system. So in this system, we lay down a loop of wire that creates a magnetic field in its interior that oscillates at a certain frequency. The receiver devices are also loops. They're much smaller, and they're tuned to resonate at exactly the same frequency as the source loop. So this system allows the source loop to transfer power wirelessly to devices that are placed anywhere in the interior or the vicinity of this source loop. And this loop is very flexible in the way that it can be deployed. You can actually make it into many different shapes and sizes, and any device that's within the vicinity of the loop will be powered. Regardless of the number of devices, you can power 1,000 or 10,000 or more devices inside this loop as long as you can fit all of them in there. And in fact, the system becomes more efficient the more devices you pack into it. So we found that we can achieve higher than 50% total system efficiency if you have a very dense array of devices packed in the interior of this loop. So the receivers are very simple. So they're a flat spiral of wire that's tuned with a capacitor to resonate at the frequency that we're using. And these receivers, here's an example of one of them. They can also be made very small and very thin. So this is just a standard FR4 PC board. It only costs about less than $1, in some cases less than 50 cents each to make each of these. And in mass-produced scale, they could be even cheaper. So for something about this size, you can get somewhere between 4 and 100 milliwatts of power out of it, depending on the field configuration. And for something larger, you can actually extract much higher power levels. So once you have this, this capability of providing power to a large number of devices within a space, then there's a lot of possibilities that are opened up that weren't available before. You can have higher duty cycle sensors, which enables real-time sensing. You can have longer range for RF communications. You can have also onboard processing of data. So if you don't need to conserve energy, you can actually use the processing processor to process data on site without sending it back to a central location. And having no batteries also enables you to make systems that work at higher temperatures where batteries no longer work. And avoiding wires allows you to have flexibility in where you place the sensors and also reduces the installation costs. So the thing that I'd like to conclude with is not really a statement, but a question, which is intended for all of you here. And this question is, what can you do when power is no longer a constraint on the design of your system? What can you design when this is no longer something that you have that's an obstacle, but if you have unlimited amounts of power to your device continuously, what is it that you can do that you weren't able to do before? So I'd like to invite all of you to come and visit our demo. We have a booth set up, booth number 17, underneath the blue canopy, and you can actually step into our wireless power environment and get a chance to see these devices in action. So please come and visit us.
Yeah, thank you very much. It's interesting when you go into an electromagnetic field with their sensors, you may possibly be able to get the monitoring world alive. At least you see that one in a very early stage with the sensors you have seen here. So maybe in the future we may see some interesting things emerge.